Polymorphism in C#, treating different types of objects as if they were the same type. The material for this presentation comes from my book, C# for Artists, The Art, Philosophy, and Science of Object-Oriented Programming, second edition with material from the third edition that's forthcoming, specifically Chapter 11, Inheritance and Interfaces, Chapter 21, Operator Overloading, Chapter 23, Three Design Principles, and finally, Chapter 24, Inheritance, Composition, Interfaces, and Polymorphism. C# supports two types of polymorphism, static and dynamic. Static polymorphism, otherwise known as compile-time polymorphism, is enabled by the language features operator overloading, method overloading, and generics. Dynamic or runtime polymorphism is all about method overriding, and the language features that enable that are inheritance, abstract-based classes, and interfaces. An object's type dictates the range of allowed operations. So for example, 1 plus 2 equals 3. That's an int plus an int. That plus operator knows how to work on two integers. 1.5 plus 2, which is a double plus an int, the compiler knows how to apply the plus operator to a double and an int. It'll convert the int to a double and return double to the, as a result of the operation. The third one's a little tricky. It's a string 1.5 plus 2, which results in a string 1.52. And so what happens is there is no, the string version of the operator, which is concatenation, right, is going to take that int, use the string representation of it, join it to the 1.5 string, create a new string, and return that string as 1.52. And finally, P1 plus P2. Now, what does that mean? Well, by default, the plus operator has no idea what to do with two-person objects, right? So the plus operator must be implemented in the person class to dictate how it should behave when you add two-person objects together, whatever that means. So this will fail unless it has been explicitly defined. Now, C# is a strongly typed language, which means that the compiler needs to know what type of object it is dealing with, or you're going to get compile time errors. Or even worse, if you try to do something dynamically, like load a DLL and you don't have the right type, it could fail at runtime if it doesn't know what type it is. Now, let's talk about dynamic polymorphism. Dynamic polymorphism, also known as runtime polymorphism. Dynamic polymorphism simply means using derived class objects where base class objects are specified. It relies on the following language features: inheritance, abstract base classes, and interfaces. Inheritance is baked into the .NET platform. You have object, which sits at the top of all reference types. So at the very least, every other reference type that you either create or that exists already in the .NET framework can be treated as if it were an object. And you see this all the time when you call the toString method on a type and you haven't explicitly overridden the toString method. There's a base behavior for toString, and it is to give the type of the object, and I'll demonstrate that when we get around to the code. Abstract-based classes are used where you only want to specify an interface or a partial implementation. Interfaces are used when you want to specify only, like in other words, there is no implementation and you just want to specify the interface to an object. Now, the difference between a class and an interface in C#, at least the most important one, is a derived class can only extend one class, but it can implement as many interfaces as it sees fit. And lastly, and perhaps the most important, is manually checking objects for their type is not polymorphic programming, and we'll see what I mean by this as we get into the code. Understanding how to achieve dynamic polymorphic behavior in your code leads to a deeper understanding of solid design principles. Solid, if you're not aware of those, are the single responsibility principle, where a class should have at most one reason to change and one responsibility. The open-close principle, which is a software entity should be open for extension but closed for modification. The Liskov substitution principle, which says subclasses should be directly substitutable for their base classes. The interface segregation principle, which suggests you favor client-specific interfaces over one general-purpose interface. And the Dependency-Inversion Principle, which says depend upon abstractions, not upon concretions. Now, let's take a look at a software architecture that implements a lot of these solid design principles. Here you have a software architecture for an application I call Fleet Simulation. It provides 3 abstract base classes: vessel, weapon, and power plant. Vessel is a composite which can contain a weapon and can contain a power plant. For the vessel, you have 2 subclasses, surface ship and submarine. For the weapon, you have 3 subclasses, 5-inch gun, close-in weapon system, or CWIS, and a torpedo. And finally, for the power plant, you have a nuclear power plant, a gas turbine power plant, and a steam plant. So, how does this architecture satisfy the solid design principles? Let's take a look. The 3 abstract base classes, weapon, vessel, and power plant, sit at the top of the inheritance hierarchy. Thus, any changes made to those abstract base classes will affect the interfaces to the derived classes that sit lower down in the inheritance hierarchy. This is the Dependency-Inversion Principle in action. Next, we have this abstraction layer made up of these abstract base classes, and this is where the code should be targeting. So for example, you'll notice that vessel is a composite of a weapon and a power plant. So within vessel, any code that's meant to execute any method on one of the derived classes will have to use either a weapon interface or power plant interface. And this is an example of Liskov substitution. A weapon will have a singular purpose. So its purpose is to act as a weapon. Weapon doesn't try to be a power plant. Power plant doesn't try to be a weapon. That's single responsibility in action there. Open-close principle, again, you've got this abstraction layer and you've got these abstract-based classes at the top of this inheritance hierarchy. And, early in the design, things may not be stable, but once you get your abstractions stabilized, then there's no need to make a modification to the code at the top of the inheritance hierarchy. Anytime you start making changes within your code, you start affecting behavior in different places. But thanks to the Dependency-Inversion Principle, we know that if we make a change at the top of the abstraction layer, it will affect the derived classes. However, once we get those abstractions solidified and locked in, then there's no need to make modifications. We can simply, let's say for example, we want to create a new type of weapon. We don't have to modify the weapon class. We just extend weapon, create a new weapon derived class type. And like for example, let's say we want to have a laser weapon that we wanted to interface with. Well, we would just create a new derived class called laser, and we wouldn't have to make any changes to weapon. That's the open-close principle in action there. Let's see how the code for Fleet Simulation looks in action. Okay, here we are in the code for the Fleet Simulation program. Let's start with the main application. I'm going to run it and we'll walk through this code. Then we'll walk through the abstract base classes and 3 of the concrete classes just so you can show you the inheritance structure. So let's hit the run button here. We'll see the output and then we'll walk through that output and compare it against the code. All right, so first off, on the first line we say power plant object created, nuclear power plant object created, weapon object created, and then torpedo object created, and then vessel object created, and then submarine object created, along with some information about the submarine, USS Norfolk, SSN 714, which was a boat I used to be on, power plant model, pressurized water Mark 85, and weapon model Mark 50. I just made that shit up. Nuclear reactor is critical, ready to answer all bells. Torpedo is locked on target. Fish in the water, heading towards target. I should have put a boom because we never miss. And nuclear plant is shut down and secured. Okay, now let's trace through the code here. On line 12, notice that I have vessel as the type for reference V1. And then I say equals new submarine, right? So vessel is an abstract base class. You can't create an instance of it. But you can create an instance of a subtype, as long as it's a concrete type and you create an instance of it. So I'm creating an instance of submarine. And in the constructor of the submarine, the very first thing I'm doing is I'm creating a new nuclear power plant, giving it a name, followed by a weapon, or a torpedo in this case, which is derived from weapon, and then the name of the submarine. Now, that's why you see power plant object created, and which is the abstract, because the abstract object, because the object has to be created, even the base, even if it's an abstract class, right, the object still gets created in memory. So you're going to see that trace. When we get to the code, you'll see I put trace in all the constructors. So as each object is created, the constructor gets called and it prints out a message to the screen, which is what you're seeing here. And then, of course, on line 15, 16, 17, and 18, when I send commands to the reference V1, it's going to print out the messages for those commands. So we get the power plant because we're going new nuclear, right, which is a power plant type. So that nuclear object gets, the constructor gets called, but before the nuclear object can be created, the base of nuclear must be created. So you get the power plant object is created, followed by nuclear power plant. And then the torpedo constructor is called, but before the torpedo object can be created, the base weapon object must be created in memory, then the torpedo object. And finally, the submarine base, which is vessel, must be created, and then submarine gets created last, right? So that's why you see that at the very bottom, at the bottom of that constructor chain call, followed by v1.lightOffPlant, which is a method call to the vessel. So let's go to vessel and see what's happening here on lightOffPlant. We see that we have in vessel, it's an abstract class, and the reason why it's abstract is because we have not implemented these methods, right? So for example, we have public abstract void light off plant. You know, it doesn't know how to light off the plant, essentially, right? So what's going to happen is we're expecting the derived vessel to know how to light off the plant, right? It's just going to have a reference to a plant. All right. So anyway, let's go into, so we got the power plant private field. Okay. Another private field for the weapon and a private field for the name. And then we have a public property for the name, which is a read-write property. And then we have a protected, so what's protected, the difference between public and protected, right, if you don't know, is protected can be inherited, public can be inherited, right, but protected is accessible to derived classes, but it's not horizontally accessible, right? So so the weapon property will be accessible to the subtype, but you can't access the weapon property directly as a client to a vessel type object, right? Then we have the constructor here. All right, so it takes three arguments, right? Plant or power plant, weapon, and string. And we set those fields, and then we just print out this console write line trace message here when that vessel object is created. So then we have the light off plant, shutdown, train weapon, fire weapon. And then we have a toString. Now the toString is overridden. So the base class of vessel, which is itself is an abstract class, is object, right? Because it doesn't extend anything. So the implied base class to every class that you create that doesn't extend some other class is object, right? So object provides a default toString method. Here I'm overriding the toString method and actually making it do something useful. All right. So now let's take a look at power plant. We'll start with power plant. So power plant is one of the classes that is required for a vessel, right? Because vessel is a composite. So power plant has a model, which is a string, has a private field, and then it has a constructor, okay, which then, sets the field to the model argument to the constructor. And then it has two abstract methods, which is light off plant and shutdown plant. All right. Now, again, it doesn't know how to light off the plant because this is just the base class, abstract base class, right? So it's counting on the concrete objects to know how to do that, right? So, for example, the procedures for lighting off a nuclear plant would be different than the procedures for lighting off a steam plant versus the procedures for starting up a gas turbine engine, all right? So, and then we override the string here as well. So it just returns power plant model plus the model name, all right? Now we do weapon. Weapon looks very similar, right? Names have been changed to protect the innocent, and it has two different abstract methods, train weapon and fire weapon. The rest of the stuff is very similar, right? So let me, I'll keep those open. So now let's take a look at submarine, since we're creating submarine. So submarine extends vessel, all right? And here's the constructor for submarine. It takes a power plant, a weapon, a string, and then it passes those incoming objects by calling the base, right? So the base constructor is then called with plant, weapon, and name. Notice that vessel or a submarine doesn't have any fields, right? The vessel object has the fields, all right? Submarine simply has, passes in those incoming arguments to the constructor and passes those argument values up to the base vessel class. And then it prints out a message that says submarine object created. All right. Now, when it comes to light off plant, this is where I say that the plant property is accessible in the derived class, right? So protected. If we go back to vessel, we see that plant, right? Here's plant. That's the property name. It's of type power plant. It's protected, right? So we go to submarine. And we're making a call when it says, let's start with light off plant. Light off plant is overridden, obviously, because this is a subclass of vessel. We have to provide an overriding method for the abstract light off plant that's defined in vessel. So go back to submarine, and it says public override void light off plant. It calls, in turn, plant.lightOffPlant, okay, which is the object that is referenced by this property here in the vessel class. And then essentially that's the same for everything, right? So shutdown plant calls plant.shutdownPlant, and train weapon uses the weapon property, which is accessible to the derived class from the base class, to call the train weapon on the weapon. So if we go to weapon, we see that train weapon is one of the interface methods to any type of weapon, right? And then, of course, fire weapon. Now, let's take a look at a power plant object and a weapon object, and that'll be it for this discussion, right? So we'll take a look at the nuclear plant, since we're doing a submarine, and the torpedo, which is the part of the submarine, right? So we'll start with the power plant. So public class nuclear extends power plant, okay? And we give it a constructor, and it passes the model up to the base, because the base power plant has a model, a private model, right? Now, so that's private. So then we go back to torpedo, right? Notice that there's no need necessarily for the weapon to access that model. Once you create the model, there's probably no need. If you wanted to have model as a field or change it to a property accessible to a subtype of weapon, then you'd have to go into the weapon and make this protected instead of private, right? Private, anything private is not accessible horizontally or vertically, right? In other words, it's not acceptable to clients of types like this or to derived types of this class. So back to torpedo. We have then the train weapon method, which is actually overridden and implemented in the actual torpedo class. And it just says torpedo is locked on target, right? So vessel, submarine, it gets the vessel just says, hey, I will take a weapon, right? When the submarine is created, it's given a torpedo, right? And that weapon. So if we go, right, if we go to submarine, let's go to submarine. It doesn't say nuclear plant. It doesn't say torpedo, right? It just says plant. So when you create a nuclear plant, it knows, this is where the polymorphic behavior comes in. I'm substituting a nuclear plant for the power plant, which is the abstract base type. And the compiler says, yep, you're a subtype of power plant. Everything's okay. Right? And then when you make these method calls, your compiler is checking to make sure that that's not going to fail, right? So that is polymorphic behavior in a nutshell, dynamic polymorphic behavior. Let's see, nuclear plant, same thing, right? So you have a model, light off plant, shutdown plant, and then again, the torpedo finally. The rest of the structure of the code is the same. I have a link below to the repository where these code examples are stored. You can download them, you can compile them, you can run them, you can play with them, you can change them if you so desire. And anyway, that's it for this particular code example. Let's talk about static polymorphism, and I'll demonstrate the employee, the person employee, right, with the payable interface next. This is an architecture for a person employee application. At the top of the hierarchy are three primary classes: person, iPayable, and employee, which is an abstract base class. The person class is a concrete class. You can create instances of person if you needed to. iPayable is just an interface, and it provides one method, payable, or pay, I should say, and we'll see that here in a bit. Employee brings together both of these, so it inherits from person and implements the iPayable interface. But in this architecture, I choose to defer the implementation of iPayable and push that down to hourly employee and salaried employee, because those types of pay calculations will be different for those types of employees. Regarding polymorphic behavior, how does this architecture support it? So you have 5 different interfaces you could possibly target: person, iPayable, employee, hourly employee, and salaried employee. The employee class is an abstract base class, person is a concrete class, and iPayable is an interface. You can't create an instance of iPayable, and you can't create an instance of employee, but you can create an instance of a person, an hourly employee, or a salaried employee. If you want to deal with employees, it makes no sense just to create a person, because they wouldn't have the pay method that's supplied by the iPayable interface. But you could still target objects of type hourly employee and salaried employee by the person interface, but you'd be limited to whatever methods and properties the person class provides in this inheritance hierarchy. Same with iPayable. So let's say, for example, you had a collection of iPayable types. Well, you can throw in an hourly employee or a salaried employee, because those are iPayable. They extend employee, and employee, even though it's an abstract base class, it says it implements iPayable, but it defers it to the hourly employee and the salaried employee classes. So they are, in fact, and this is a relationship, iPayable types. You could have a collection of person, right? Like a list person. And you could create instances of hourly employee and salaried employee. But like I said earlier, you would be limited to the interface provided by person. You could create a list of type employee, which is probably in this relationship the best interface to target because it brings together person and iPayable. If you created a list of hourly employees, then you would never be able to mix and match, right? You'd always have to just put hourly employees in that list. Same with salaried employees. You could have a list of salaried employees, but you would never be able to put in an hourly employee, right? For polymorphic behavior, the goal that you're after is to treat different types of objects the same. In this particular inheritance hierarchy, if you wanted to access an hourly employee and a salaried employee and, find out what their name is, call the pay method, and whatever else employee brings to the table, then the employee interface is the one that you want to target. That's the abstraction you target. So let's take a look at some code and see this whole thing in action. And here we are in the code for the person employee example. I'll start by running the program so you can see what the output is, and then I'll walk through the main application code followed by person, iPayable, employee, and then hourly employee and salaried employee. The key takeaway, this section will focus on the dynamic polymorphic behavior, and then after the static polymorphism presentation, I will then return to show you how to overload an operator, use it in generics, etc. Okay, so we have an output of P1's full name is Coralie Sarah Miller, and then Alania Alexandrovna Ivanov, I had to go look that one up, will be paid $2,480. I left off the dollars off of that one, I have to fix that. And Ulysses is 49 years old. He will be paid $10,000. Okay, so let's take a look at the code here for the main application. Now, essentially with that architecture for person employee example, you've got person, which is a concrete class, so you can create objects of type person. Then you have iPayable, which is an interface. You can't create objects of an interface type, but you can create, any concrete classes that implement that interface. And then finally, you have employee, which is a abstract-based class, and you can't create an instance of an abstract-based class, but you can certainly create one of the derived classes that implement the or that extend that abstract-based class. So let's start at the top. We have person P1 equals new person. Okay, so fill in the constructor. And then then I have this console write line. P1's full name is P1. So P1 is person. I'm just feeding in the reference here, and the write line, or that string concatenation operator, is calling the toString on the P1 reference, which is a person. So let's go to the person class, and we see that I've overridden the toString method, and it returns first name, middle name, last name. Okay, so let's go back here to program and take a look at the output one more time. And it says P1's full name is Coralie Sarah Miller. So that's where that Coralie Sarah Miller is coming from the P1 overridden toString method or person class. Now, iPayable, I can create a reference to an iPayable. And let's go back to line 13. So person P1 equals new person. I can create a person object, right? If I tried to create an iPayable, or if I tried to create an employee, I'd get a problem here, because a person is at the very top of the inheritance hierarchy, and it is not a payable or a salary or an employee or a salaried employee, right? It's at the top. So I can only create person objects, which means I can only target the person interface that the person class publishes or supports, right? So iPayable is the next interface on line 22. So iPayable is payable. Payable one's a reference, And now here I create a new hourly employee, and I fill in the constructor. Okay, so then on line 29, I have a console.writeLine, payable 1. Now, this is the interesting part, right? If we come down here, we'll see, let's do payable 1 dot, and IntelliSense will show us what methods we can call. We can call the equals, get hash code, get type, toString. Why? Because they're object, right? But because it's an iPayable, I can also call the pay method on it. So it'll call toString because everything extends object essentially, right? Eventually, down underneath the covers in the .NET runtime. So when I pass in payable here, payable 1, it'll call the toString. So that'll result in the full name, will be paid, and then payable1.pay. Okay, and I'm dealing with an hourly employee here, so whatever the hourly employee pay calculation is, let's take a look at that. Hourly employee, I have some specialization going on here. Hourly employee extends employee, which is an abstract class. We haven't looked at it yet, but we will. Has 2 private fields, hours worked and hourly wage. Okay, and then 2 public properties. These are horizontally accessible. And then a constructor which takes in a series of arguments and then passes those arguments up to the ones that are needed by the employee class. It passes those arguments, which is first name, middle name, last name, gender, birthday, and employee number, up to the employee base class, and then fills in the hourly employee specific fields in the body of the constructor. And then here I've simply overridden the pay for an hourly employee. So for an hourly employee, it just simply returns the number of hours worked timed hourly wage fields. Very simple. This is not going to be used in any real accounting system. This is just for demonstration purposes only. But this is going to be called, so I think maybe now let's just take a look at employee, right? So employee is an abstract base class, obviously. Person, it extends person and implements iPayable. Remember, in C#, a class can only extend one other class, but it can implement as many interfaces as required. So it extends person. I think it's worthy to pause here. Let's say that you want to get more into software architecture design. That really that's one of your biggest design decisions right there is, how are you going to structure your inheritance hierarchy? Which classes are going to extend which other classes? Or should you target interfaces, right? That's not necessarily a trivial question to answer with regards to design, right? I have no answers. Every application will have its own unique requirements and challenges. What you want to try to avoid is programming yourself architecturally or designing yourself into some architectural corner that's hard to escape, right? Which then starts leading to breaking the rules, et cetera, et cetera. That's what you want to try to avoid. And that comes with experience. And hopefully, if you're a junior and you want to learn this stuff, you work with a good senior people who've done it and are good at it, and they teach you the tricks of the trade. So employee does provide specialization over person in that it provides an employee number, which is a private string field, and then it provides a public employee number property. And then it has a public constructor, which then passes up all the different arguments to the base class, which is a person. First name. Person requires a first name, middle name, last name, gender, birthday. And then it sets the employee number here in the constructor for the employee object. And then this is abstract, right? This is the reason why this class is abstract, is because we say we're going to implement iPayable, but we actually push that off, right, to derive classes. So we're still going to call this abstract, public abstract double pay. So we essentially we're mapping the payable.ipay to an abstract method and defer implementation. That's why this class employee is abstract. We're saying in our design, push it down farther. Don't look for an implementation here. one of the subtypes is going to have to fulfill this contract. So that's where hourly employee comes to the rescue. It extends employee. Notice it doesn't have to implement I payable, because employee implements quote unquote I payable, which is the pay method, but it defers the implementation down to the derived class, right? So at some point in that inheritance hierarchy, pay has to be implemented somewhere, somehow. And here in the hourly employee class, we provide such an implementation. Same for salaried employee. Salaried employee provides a bit of a different type of calculation. We simply take, it has one field instead of two, just a salary, and then it has a public property. The constructor is going to look very much the same, with the exception of it's only setting one salaried employee specific field in the body of as opposed to hourly employee, which has two fields, right? But it overrides the pay method and returns salary or underscore salary divided by 24, right? Some goofy calculation there. Now, I payable, I should have went over this earlier, but I payable is simply just an interface, and it provides a declaration for a method called pay with obviously no implementation. That's really when you want to use an interface, is there's no implementation and you just want to specify a contract of dealing with some type of an object. So once again, back to the program, we are targeting payable in this one, right? And then finally, we target employee. Employee is really the target abstraction of choice in this design for the person-employee inheritance hierarchy, because you get everything, right? If we come down here and we look at IntelliSense, we have employee 1, and we hit a dot, right? And we get everything that person provides, plus we get what pay, what I payable provides, and then we have access to the employee number, which is what the employee class provides. Okay, so that's really if you want to deal with everything as a single type of object, you target employee, right? So I could have another, so employee, right? I'm just creating a salaried employee here, whereas up here for I payable, the payable 1 on line 22, I created an hourly employee. Here I created a salaried employee. After the static polymorphic part of the video, I'll have one more demo where I show you how to use generics and method overloading and method overloading, operator overloading, and generics to achieve static polymorphic behavior. And I'll use this code as an example for that. Anyway, that's it. Static polymorphism, otherwise known as compile time polymorphism. Operator overloading. Operator overloading simply means defining operators that work with your types. There's a handful of operators you can overload. Those are defined in the .NET framework documentation. And you've seen an example of the plus operator, right? The plus operator can be used as a unary operator on numerical types or binary operators. And I already showed you how those work earlier in the video, so I'm not going to redo these. But you can overload operators on your user-defined types to give them meaning in the context of your type. Method overloading. Method overloading means having multiple versions of the same method with the same name with different argument types or count. So you use this all the time. For example, system.console.writeLine can take a string, it can take an int32, it can take a double, etc., etc., etc. You can overload constructor methods as well as ordinary methods. Generics. You first encounter generics when you use the system.collection.generic namespace. And if you're new to C# programming, those class definitions and function definitions look rather cryptic, with the angle bracket and the T, or perhaps a T, comma, U, or even more type parameters. Anyway, that capital T is what's referred to as a type parameter. And it allows you to specify the type of object that you're going to store in the collection. Back in the day, and early days of the .NET framework, the collections framework only took object in and object out. That means you had to kind of keep track of what you'd stored in the collection, and then when you retrieve the object from the collection, you had to cast it to the proper type explicitly. The generics and the type parameter allow you to specify the type that goes in, and then the compiler will know what type you're going to retrieve from the collection. You can use type parameters in your code. You can create generic classes and generic methods. However, just to be aware, if you don't specify what's referred to as a type constraint, then you're going to be limited to just whatever operations you could perform on system object. So for example, if you have a class declaration like class, my class, angle bracket T, and you don't have a type constraint, then you can't assume anything in the body of your code other than object. In other words, you can't call interface methods for a type other than what object specifies. However, if you add a type constraint, then you tell the compiler, at the least, the base type of the objects that will be stored in my class, represented by T, will be an employee type. Okay? So that's how you specify a range of operations for the types that your generic classes and generic methods will contain. Hey, here we are in the code for a demonstration of static polymorphism with the person-employee architecture. Now, I'm in the program here, so this is the main method, obviously, and I went through the creation of a person object, an IPayable object, or an hourly employee object, targeting a IPayable interface type, right? So, and then next, an employee reference, and I put a salaried employee pointing, that reference points to a salaried employee. All right, so I have those objects that I can play with, and now let's demonstrate polymorphic behavior, or static polymorphism, to be more exact. Let me run this program first. I'll explain the code in the program.cs file, and then we'll go through the person, and I'll show you how I overloaded the operators for this demonstration. All right, so first let's hit run and see the output. And I'll make this bigger so we can see it all. Coffee in the morning. All right, let me make this bigger. All right, so we have the output from the original. Now, what I did do is I changed the toString method in person to give all the stats pretty much for a person. So we see that here. That's going to be different from the previous demonstration in this video. And I'll go over those changes. I wanted to print out not only the full name, but the sex of the person, their date of birth, and their current age. Now, demonstrating overloaded constructors. In the person, there's 3 overloaded constructors. So again, the compiler knows which constructor to call based on the number of parameters and types. And you can obviously overload not only constructors, but you can overload regular methods as well. So this is just demonstrating 3 different types. Now, when I get to the code, well, let me see. Here in person, we see that P2, and the program, in program.cs on line 55, we see person P2 equals new person. That is the default constructor. And then I just do a console.writeLine P2, and that prints out John J. Doe, male, born, and today's date is January 21st, 2022. So behind the scenes, the constructor just says, all right, you didn't give me a date. I'm just going to use datetime.now for the birth date. Okay, and then age is obviously 0. Now, the 4-argument constructor is next, and it takes first name, middle name, last name, strings, 3 strings, and then the gender, so person.sex.male. And then console.writeLine P3. These are all people objects. So Rick Warren Miller, male, born 1/21/2022. Again, I didn't give it a date, so it just gave it today's date, age 0. And then finally, P4 equals new person, Edgel Victor Miller. That's my grandfather. person.sex.mail, new date time 2002, July the 4th. Now, and then over in the output, you see Edgel Victor Miller down here. Male born 7/4/2002, age 19. Obviously, he's not 19 years old. All right. Now, demonstrating overloaded operators. Here, I'm doing a console write line on line 68. It says, P2 is P2 name older than P3 name? And then I go P2 greater than P3. Yes, no, that's a, what is it, a try operator, logical operator. I can't even remember the name of it. Okay, so then in the output, we say, is P2.name older than P3.name? And no. And then next line is P2 name younger than P3 name? And the answer is no. And the next one is P2 name the same age as P3 name? And then we use the equals operator, and it says, oh yeah, they're the same age. All right. And then finally, demonstrating generics. I targeted IPayable on line 74 for the list. So I made a list. I declared a list of IPayable, named it employee underscore list, and said equals new list IPayable. And the reason I did IPayable was because I had an IPayable up here already that I could use on line 23, IPayable. So I had a payable one reference, and then I stuck in a new hourly employee. So that payable reference points to an hourly employee object. So I'm going to come down here, and I figured I'll just make that IPayable, and then I can stick in payable one and employee one. The ramifications of having an IPayable is, you don't know that you're dealing. It doesn't matter what type of object it is, as long as in that inheritance chain someone implemented the IPayable interface, right? So it could be an hourly employee, salaried employee in this current architecture. It could be anything. Any object could implement IPayable for whatever reason, or any class could implement IPayable. And so you're really limited to the pay method here, and then whatever object brings to the table. So in this case, obviously, the object that, and then again, you don't even have to worry about this stuff, right? You're just targeting an interface, and whether or not, that interface is going to implement the toString method, you don't really care, because either object is going to provide its default implementation, or whatever the class or the object that you actually are dealing with may override that, right? In this case, person overrides the object's toString method, and we saw that in the last video on the person employee. So the output for each of this for each will then go through the list, right? And will print the following line. It said P plus, concatenate will be paid, and then I'm using some string formatting to convert that to currency, comma, p.pay. So just call the pay method on each of these objects in that list. And then at the very bottom of the output, we see the Russian gal gets female, born, her date of birth, her age will be paid $2,480. And then Ulysses S. Grant, a male, born 7/14/1972, age 49, will be paid $10,000. And if anybody deserves $10,000, it's Ulysses S. Grant. Now let's take a look at the person class and see how we actually overrode these operators. Well, let's just walk through the constructors first, right? So obviously this is overloaded operators is one form of static polymorphism, and of course you can overload constructors. So the default constructor is provided. That means you can just create an object of type person with no arguments, but it will then call this constructor, right? Which means look for another constructor with 1, 2, 3, 4, 5. So it goes down here and calls this 5-argument constructor. Everything pretty much points to the 5-argument constructor in the end, right? Even the 4-argument constructor. So the next constructor, which is overloaded, is you can create a person with 4 arguments: first name, middle name, last name, gender, and then leave off the birthday, and it will supply datetime.now as the birthday. which means it's going to call the 5-argument constructor anyway. Or you can just skip to the head of the class and call the 5-argument person constructor and give it a date of birth if you know what the date of birth is. Here's the modifications I made to the toString method. I'm just returning first name plus space, middle name plus space, last name plus, and then a little pipe character there, plus gender, and then another pipe born, date of birth to short date time string, plus, and then pipe character age, colon, and then the age, right? So I added some more statistics to that toString. If you didn't want all those things, you could override toString in the derived classes and provide whatever the heck you want for those types of objects. You could add the pay for an hourly employee or salaried employee, right? In the employee class, you could provide the employee number, okay? Or the employee ID, whatever that field is. Now for the overloaded operators, let's take a look here. In my book, C# for Artists, Chapter 21 provides a list, and you can find this obviously online in the .NET documentation, the overloadable operators. What you need to understand is some of these must be overloaded in pairs. So I overloaded the comparison operators, and these must be overloaded in pairs. So in other words, if you overload the equals equals operator, then you must overload the not equals operator. If you overload the less than, you must overload the greater than. And then finally, if you overload less than equals, you must overload greater than equals. So that's why I chose those operators. So back to the code, we see the less than, equals, and greater than equals operator here. So the first one is the less than, and simply you're dealing with two-person objects, or you could have like a person and an int, or whatever, right? But for the most part, I'm dealing with person objects. I'm comparing two-person objects. And then I call these left-hand side and the right-hand side, right? So what you do is essentially something has to boil down to some primitive type, I believe, or some calculation that you can actually wrap your head around, right? So in this particular case, I just return left-hand side dot age less than equal to right-hand side dot age, and these return a Boolean value, obviously these comparison operators. And then if you overload this, it'll warn you, right? So let me see, if I comment this out, let me see, edit, toggle, well, I'll just go ahead and do it manually. If I do this, that, and that, right? Now, you see this red warning here underneath of the less than, and if you hover over it, it says person.operator less than equal, person comma person requires a matching greater than to be also defined, And that's just telling you that these things must be overloaded in pairs. I'll save that. So there's your matching pair of operators, less than, equals, and greater than equals. And then next I did greater than and less than. And then finally equals equals and not equals. Now in the context of person, I figured age was the appropriate thing to compare. Your design for what you're doing, obviously you'll have to put some thought into how you want your objects to behave. There's a whole chapter in my book on how to actually consider how you want your objects to behave. If you're going to use person objects in comparisons, you really should overload the compare to operator, or iComparable is the name of the interface, right? If you really wanted to use these objects in like sorting, right? If you want to sort, you need to implement iComparable, right? I have not done that here. But that is something that you can certainly consider. But anyway, that's pretty much it for the static polymorphism piece. So yeah, on to the end of this video.